and beep out certain portions, since I have the chance to do it. All right, so getting back to the homework assignment. Okay, so this homework assignment is kind of interesting because we don't really see C subroutines like this, every day, but it is capable. Okay, this is one of the things that C is capable of doing. So the question now is, okay, let's find out what it does. It takes, okay, how many parameters is find max n taking? That's the first question, which is already a trick question to begin with. The syntax of this is saying int x, on line 2, it says int x comma dot dot dot. Okay, so it is a valid syntax. The C compiler has no problem with this type of syntax. In fact, this is in the very, very, very early version of C already. Okay, so this is not a late feature. This is a very early feature. What it is really saying is that we have any number of parameters. Okay, x is just the first one. Okay, but the other ones do not have names. You can see that I cannot refer to the second parameter by name. So how do we refer to those things? So that's why when you look at the program itself, when you look at the subroutine, it has a local variable which is a pointer to an integer. It has its local variable max to keep track of the maximum of the numbers that it has seen so far, and it is initialized to the first number. Okay, and then we initialize the pointer to the address of x. And here's the interesting part. If you look at how it keeps popping up that, it's because I have a certain plugin installed, and every time I start Firefox, it would check all the plugins and update everything. So while whatever the pointer points to is not the minimum integer, which is defined in limits.h, it will keep going like this. And when you look through the code, the last line is the interesting part. It just increments the pointer. So what's happening here is when you push arguments on the stack, it goes like this. The first argument, or the last argument, I should say, this is high memory location. The last argument is pushed first. Then the second last argument is pushed, and then so on. So when you look at it this way, the first argument is the one that is pushed last on the stack, which means it has the lowest address. But all the arguments are contiguous on the stack. And that's why we can use a pointer based on the address of the first argument and be able to get to the other ones. Are we kind of doing okay so far with this code here? So we push the arguments, last argument first, and then we go all the way to the first argument, and then the call happens from the caller. So the return address is here. So if I were to, this is argument, if you prefer 0, because we like to count from 0. And then after the return address, we get to the subroutine itself, and then the first thing the subroutine does is to save the old EBP. So then old EBP is here, old EBP, and then after we save the old EBP, if you have any local variable, then the local variables are defined down here. So these would be my local variables, and which your current, the homework assignment that is due today, has this particular element, so you should probably know that part also. So that's how the stack frame is actually set up, and it's pretty universal. Okay, with GCC, this is exactly how the frame is set up for every single subroutine. So are there any questions about this picture, or how find max n works? Okay. How many people know about Printf or scanf, before this class? Have you ever wondered, how it works? Nope. It's just accepted. Yes. So the way it works is, it has one single parameter that is mandatory, which is the format string, right? And in the format string, what Printf does, it scans the format string for %d, %x, and all the other format stuff. When it finds one, it goes to the rest of the parameters and say, oh, okay, you are next. You must be the integer to fill that particular placeholder, and so on. And that's how Printf works, which is a very, very different mechanism compared to C-in, C-out. Because C-out is completely object-oriented. Okay, it uses the left shift operator so that you can specify what you're printing to C-out. Okay, and that's very, very structured because the type of what you're printing dictates which overridden function it is going to call, because there are multiple operators defined already, and each one for one type of thing that you can print. Okay. All right. So I think we are almost there. So I'm going to switch screen. I'll leave this on the board because I think it might be helpful for the question, and I'm going to switch the screen to the quiz of today. I'll give you time. I'll just kind of wait until you guys are done writing. So let's go ahead to go to the quiz for today. Here we go. So now it is open, and this is, I want to be able to display the whole thing, and it's not easy. Okay, I know what. Okay, so I'm going to read the question first. This is not a speed test, so don't worry. I'll give you guys enough time to do it. The stack is used for parameters and local variables, but it is also used for bookkeeping items like the return address and the saved EBP, just like what I have here on the whiteboard. This means that overwriting memory locations on the stack can result in some very interesting behavior. This is actually going back to the very first program that I showed you guys, at the beginning of the entire semester. How you can mess up a program strictly in C and have a behavior that cannot be explained in C at all. Examine the following program and indicate what kind of problem may result based on what we have discussed in this class, and also what we have just talked about here on the whiteboard. You may assume there is nothing else on the stack other than parameters, local variables, return addresses, and saved EBPs. So you don't have to say, oh, but what if the compiler decides to save EAX on the stack, in between these two local variables? Don't worry about that. These are the only things you have to be concerned about. Furthermore, you may also assume that a local variable declared earlier has a lower address. So in this case, in main, because int x is encountered before int y, so x as a variable is going to have a lower address compared to y, and it's contiguous. Okay, is that okay so far? It's kind of like what you did with the homework assignment that was due about 15 minutes earlier. If you have two local variables, then the two local variables are right next to each other. There's nothing in between them. There are no gaps. In this case, x has an address that is lower than the address of y because x is declared first. Okay, so that's what that sentence really means. Note that the call to exit is the same as system surface number 1, which is all we do in our assembly language program. At the end, we put a 1 into EAX and put something into EBX as the exit code, and that gets you out of the program right away. This main does not return. Okay, it doesn't get a chance to get to any return statement because the exit call is actually going to terminate the entire program. It's going to terminate the process. And the question is specifically what is the exit code of this program, which is not really the most important part. The most important part is you have to explain why that is the exit code. Okay? Because I'm pretty sure most of you can figure out the exit code can only be one of a few numbers, that are on the projector, right? So that's not really the main question. Is can you guess the right one? The main question is, can you explain why it is going to have that exit code? Is that okay so far? Okay. So the only part that is tricky, if you look at main has absolutely nothing tricky at all. Okay, we have local variables x, y. We have assignment statements, a call to saboteur, and exit. Okay, nothing really suspicious at all. So that means the only line that is suspicious is line 5, and line 5 is a perfectly okay statement in C or C++. You can actually do this in C++ as well. The question is, what exactly is it doing? Okay, so you have to tie in the effect of line 5 inside saboteur to what we have been talking about in this class as far as what is on the stack, what is in the frame is concerned. Okay, that really is the question that you have to answer. So I'm gonna leave it to you guys to, yep, go ahead.
So you want to know the value of x at the exit?
Pretty much, what is the actual exit code and why that is the actual exit code. Okay. So your explanation probably will involve, how things are arranged on the stack, and why certain types of overwriting of locations on the stack can cause issues somewhere. And you can certainly draw a picture, on the piece of paper first, to help you kind of understand how things are laid out, and you know what, this is going to do some nasty things to that.
X equals 10 down the main. Is that 1 0 or 1 8?
That's a 10. That's
Okay.
a 1 0. Okay, I'll give you guys a hint. You have to start thinking from the perspective of main first. Okay, so think about the call frame of main. Where are the local variables? Somebody's calling main, okay, for sure. Okay, because main is really just a subroutine called by some code that you cannot see. Okay, so when main is called, okay, what do you see on the stack? What is the first thing or the top thing that you see on the stack as far as main is concerned? When main gets control, what is the first thing on the stack? The return address. Okay, the return address, because even though main does have parameters, I'm declaring that it does not. So as far as this main is concerned, I'm assuming there are no parameters whatsoever, right? So the first thing that I can count on, in this case, because I say that main has no parameters, the first thing I can count on the stack is really just the return address, because main is a subroutine, right? It is prepared to return to its caller. So main is going to have a return address, which is at the highest memory location, because the stack grows down. Okay, as we push and call, the stack pointer goes lower and lower. And then it has two local variables. But wait, hold on a second here. We cannot allocate for local variables just yet, because one thing has to be saved before we start to mess around on the stack. What is it? The frame pointer, right? EVP. So the frame pointer that belongs to the caller of main is going to be saved. So that from this point on, I can now mess around with EVP. All I have to do is to restore that, and then my caller will not know what happened to EVP. Is that okay? Okay. And then what happens? What do I do on the stack? I have two local variables. So we're going to have to allocate for the two local variables. Now, because in the text I already described, if a variable is declared first, it has a lower address. So that means, y is going to be at this location, and x is going to be at this location. Local variable x and y of main will be arranged like this on the stack. Is that making any sense? They're right next to each other because they're both local variables. But in the text I already described, the convention is if a local variable is declared first, it has a lower address. Okay? And that's really a convention. It's not a standard in the C standard. It's just a convention used by most compilers. Okay? So this is the call frame as far as main is concerned. So main is going to say, oh, y gets 4, which means this location gets the representation of 4 in 32 bits. So 4 is going to be here, and x gets a value of 10. So the 32-bit representation of 10 is going to be here. Now each time you see a block here, it is representing actually 4 bytes. Okay, I just don't think that it's necessary to use 4 individual blocks here because everything is a 4-byte thing. So I just use one item on the whiteboard to represent 4 bytes. Okay, so now we are on line 4, or 14 actually. It doesn't show the 10, the teen here. So this is actually line 14. It calls Salvatore, okay? So when it calls Salvatore, it has a parameter to pass. Where do we put the parameter? On the stack, okay? So we just push 4 on the stack, so that's fine, okay? So 4 is going to be pushed here, which is the parameter to Salvatore. And then what do we do? After we push the parameter, we call the subroutine, right? So when we call the subroutine, the side effect on the stack is it will save the return address. Okay? So we save the return address, but this time it's the return address going back to main, okay? Because it's main calling Salvatore. Salvatore has one single local variable y. But wait, we cannot do anything about the local variable y just yet, because we have to save something first. What is it? EVP, right? Okay, so we are now saving O EVP on the stack. And by the way, whose EVP is it? Who was using this EVP? Main, okay, so keep an eye on that one. And then we allocate for the local variable y. So local variable y of Salvatore is going to be here. And that pretty much, completes the picture of the frames, 2 frames, one belonging to main and the other one belonging to Salvatore as far as this question is concerned. So if I were to use a different color, then I can identify and say that this part here belongs to main and this part here belongs to Salvatore. In other words, I'm classifying the parameter is also belonging to the subroutine being called because that's the one that is using it. Okay, the caller has no use of this parameter. It is the callee, the subroutine being called, that needs to access this location. All right. So now that we know the stack looks like this, the question now is, what is line 5 actually doing? Line 5 is saying, I'm not going to modify y. I'm going to use the address of y to get to a location, and then change that location by whatever the value of the parameter x is. That's what it's doing. So y is here, and I'm not changing y, I'm changing the location after y. And this +1, you have to be careful because the address of y is an address of an integer. When you add 1 to the address of an integer, you're not just bumping up by 1 byte, you're bumping up by the size of the integer itself. Okay? That's pointer arithmetic in C. Okay, and we are bumping it up by the amount of x. So I'm pretty sure you know by now which location is getting modified. Okay. All right. So it is getting modified. We know by how much it's getting modified as well. The question is, does it impact Salvatore at all? Yeah, not really. Salvatore doesn't care, right? Except at the end of Salvatore, it would do one thing before the return. What does it do? What is the exit code of a subroutine? The first thing is it copies EBP back into ESP, and and then it will pop EBP so that it will restore EBP of the caller, and then it will do the return. Okay, those are the three instructions at the end of every subroutine. Okay, so now the question is, what is the side effect of those three instructions now that we have messed around on the stack a little bit? What do you think? Okay, first of all, which thing on the stack is actually incremented by 4? No, it's not the return address. It is the one thing after Y.
Oh.
It's EBP itself. It's old EBP that is getting changed. Because the address of Y is pointing here. So the address of Y plus 1 is referred to this location. So now ODBP is not changed a whole lot. It is only off by 4. Okay. So by the time we get to the exit code of Salvatore, it will pop this back into EBP, the register EBP itself, right? And then we'll do the return using this return address, which is not modified. The return is going to work just fine, not a problem. So when it does return, it will return to line 5 of main, because we continue execution after the call. Line 4 is the call, line 14 is the call, line 15 is where we continue to execute. So the question now is, from the perspective of main, what used to be referred to as X, is that really X at this point? Because the compiler generates code just like what you do in your homework assignment, okay? It uses EBP as a fixed point and rely on that point and say everything is relative to where EBP points to. So now that EBP is off by 4, what used to be X is now what? Is now Y, okay? So by referring to X in main, it is now actually referring to Y. So the exit code of this program is going to be 4, not 10. Okay. If you have variables declared, they're all, let's say they're all integers, X, Y, and Z, then referring to X in the code is actually referring to Y in storage. And referring to Y is now referring to Z in storage. So everything is now off by 4. Yep.
Isn't that a plus equal? So would it add?
This one here?
Yeah.
Yeah, it is a plus equal.
So would it add 4 to the value of Y?
No, it is adding 4 to the frame pointer itself. So when main is using the frame pointer as a fixed point to access its own local variable, everything is now off by 4. And this is
between the 4 that's between the two. I mean, it's reading the 4 that you passed as an argument.
yes, because in the argument I specify 4 here, and that's why it's off by 4.
It's that 4.
It's that 4, right?
Not the other 4. Not the
No.
other 4.
No, if I make this 14, it would have returned 14.
Yeah.
If I initialize
Maybe
Y to
that Y is
14, if I initialize Y to 14, it would have the exit code of 14.
The Y on the stack is 4 away from.
Okay. Let's think about it in another way. When main is running, okay, what is the proper location of where EBP should point to? ODBP, right? So this is the proper place for main to point to.
Right.
When it is in execution, this is where EBP should be pointing to. Okay? When Salvatore runs, then Salvatore should change EBP so that it points to the old EBP of main.
Yeah.
Okay. So on line 5, when we increment the thing after local variable Y by 1 by 4, what we're doing is now we're taking this number, ODBP, and we're just adding 4 to it.
Yeah.
Okay. So ODBP is now ODBP plus 4, and it doesn't do a single thing to Salvatore itself, because Salvatore has no use of this location other than restoring it at the end of the function. Right. But when it is restored, back to main, EBP is no longer pointing here. EBP is now pointing here. But everything is accessed relative to EBP. So as far as main is concerned, excuse me, as far as main is concerned, it understands X is 8 bytes below where EBP points to. And when it gets to line 5, it would keep that understanding that X is always 8 bytes below where EBP points to, not knowing that EBP is no longer pointing to the right location. So that's why, when it's attempting to access X, it would end up accessing Y. And you can turn the answer into, I will count it for grade. It's kind of like taking roll, with your, answer. But does everybody understand why the program is going to behave in that really strange way? And it's all caused by, changing something on the stack that your program should not be changing. But you can see that I did not even drop down to, excuse me, I did not drop down to assembly code. I'm using completely legitimate C code here, and yet I can do something that nasty. Okay, so the next question is, who is going to be so crazy to do something like this? And the answer is no one, right? No one in their sane mind is going to do something like this to their own program anyway. But how many times, sorry, go ahead.
I was just wondering if you changed the argument for saboteur to like 2, would that give you a value?
That it will be in between?
Yeah.
Which means it will give you, if it's 2, then it's going to grab half of X, the upper half of X, and the lower half of Y to be quote unquote the new X. So it'll be a much larger number because the lower half of Y is going to contribute the 4, but let me think. It will take the upper half of this as the lower half, so it's going to be 4 0 0 0 0. That's going to be the actual value you'll be accessing, because this comes from the upper half of X, but because X is only 10, so the most significant 16-bit will be zeros, and the lower half of Y is 0 0 0 4. And that becomes the most significant 16 bits of the actual value that we'll be accessing. So if you change the 4 on line 14 to a 2, then the exit code is going to be 40000 in hexadecimal, which makes it even more, well, it's actually, with this, it's easier to spot the problem. But with only 4, it's much harder to spot the problem because it looks like, hey, how come everything is shifted by one variable, right? Okay, so getting back to the question of who's going to be so crazy to write this kind of code and run into this kind of problem, the answer is no one is going to write this kind of code intentionally to get into this problem. But we can get into this unintentionally. Okay, every time you declare a local variable that is an array, and you access the array out of bound, and it involves like addition or subtraction, this can potentially happen. Okay. Now this is really unfortunate because if you mess up the return address, let's say we 0 the return address, okay, we just put a 0 into the return address, the problem would happen at the end of saboteur. In other words, the saboteur committed suicide, which is not a big problem, right? But when you mess around with EBP, saboteur itself is going to be okay. It's when you get back to the caller and restore the modified old EBP back into the register EBP, then problem starts to happen. But by the time you have symptoms to show you that, hey, the values are all out of whack, it's already way past the point of calling saboteur. And at that point, you look at all your variables, they'll all be shifted by 1. And then it will look like, what just happened here? Is the debugger broken? Is the compiler broken? Exactly. But it does happen, okay? I ran into this a long time ago, and at the time I did not understand, what is underneath, a C program, and I could not explain it. I just could not explain why the program is behaving very strangely, okay? Everything is off by 1 byte, it's like, or off by one variable, and I just couldn't explain it. But it can happen, okay? Especially when you use arrays of integers as a local variable, and you access the array out of bound, and you do some computations to those numbers, this can easily happen. Okay. Any other questions? Yep.
Have you ever made a program using this to mess with people?
Just did. Exactly. Yep. Exactly.
Because it still works, right? It just sends out a different exit.
Well, okay, it quote unquote works, but if it is not main and you're returning from this subroutine, then it will crash. The caller of Saboteur is going to crash because Saboteur main is no longer having the return the EBP pointing to the right place. So when it returns, it will use the wrong return address to return, and then it will crash. But the problem is, it's not the code, it's not the subroutine that contains the problematic code that is crashing, it is the caller that is crashing. Now, if you think about this a little bit, let's say you have a call hierarchy, a call tree of, I don't know, let's say 6 levels deep, which is not too bad, okay? So in other words, main calls a subroutine, it calls another subroutine, it calls another subroutine. So we have a hierarchy of 6 of them, okay? And this instruction here, okay, line 5 is not, %y plus 1, but that 1 becomes, like a larger number, okay? Let's say, 25 or something like that. Then it'll be even worse because it's not going to mess up the caller. It's not going to mess up the caller of the caller. It's going to mess up the caller of the caller of the caller of the caller of the caller. So when code gets all the way back to the point where the modified EBP is going to be utilized, you'll be so far away from the actual cause of the problem that even if you understand this type of stuff, it will still be very difficult to find out who is responsible because it became a time bomb, basically. This one is like, you set a bomb, you just walk away, 5 seconds, it sets off, okay? But in the case of, changing this 1 to like 15 or 20 or a larger number, it becomes a much longer fuse. So by the time you experience problems with a program, it is way past the point where the problem really is. And that type of problem is very hard to debug. It's just, nasty to get into that type of situation. And this really is the purpose of this class. As far as I'm concerned, this is one main purpose of this particular class, is so that you guys have an understanding of what is underneath the C code, how C code actually executes as low-level instructions, how memory is organized, and how a program can be messed up in a way that cannot possibly be explained if you just understand C and C++. Kind of gives you an X-ray vision to your C programs.
So hypothetically, you couldn't change any of the body of the Saboteur subroutine? Would the best way to readjust things between lines 4 and 5 just to subtract from the base pointer at that point? I mean, as long as you just subtract forward again from what you've added,
right?
Would it just readjust everything back to where it needs to be?
You mean inside Saboteur itself?
No. If you couldn't affect the body of Saboteur,
okay.
If you just do stuff between the call to Saboteur and the call to exit.
There's no way main can do it because main has no ability in C to modify EBP.
I'm just saying hypothetically, wouldn't the way to rectify this just to add 4 back to the base pointer?
Correct.
Or
EBP, which is the base, which is the base pointer.
And it's subtract, yes.
Yeah. Mm-hmm.
Okay.
Yeah, but C has no way to do it, and it does not even know it has been modified.
Doesn't have a way to access assembly within the C code?
You can do inline assembly, yes you can, but it's hard to even recognize that you have a problem.
Sure.
So this means, when you run into problems like this, the first thing you do, okay, so if you're in the subroutine, you call something, and you come back, everything is all messed up, the first thing you want to do in GDB is to put a breakpoint there, rerun the program from the beginning. But right before the call, you take a look at ESP, EBP, and all the other registers, and then you call the subroutine. When it comes back, look at all the registers again. ESP should not have been changed. EBP should not have been changed. The other registers, yeah, I mean EAX, ECX, and EDX, they can all be changed. I mean, those are all free to other subroutines. But ESP and EBP are the key ones. They should not change when you come back from a subroutine, at least from the C perspective. Yep.
So if you put a saboteur at the -4 below, or at any point before the exit, that should also balance
Yep.
it?
Yep. If you put a -4 as the parameter, as the argument to saboteur, then everything will be because EBP will now be pointing here, so your what you think is Y will now be your X. And what you think is X is going to be the parameter of 4, so it will still have a value that seems to be reasonable, but that's only because this is a leftover from the call itself. I'm kind of surprised that no one is saying, attack, I don't believe it. You got to show me, this is actually what the program is going to do. Okay.
You wouldn't lie to us.
Well, not intentionally. That's the worst part of it, right? I'm not doing it intentionally, so I can't even. You cannot tell from my facial expression. It's like, oh, tech is lying. It's fibbing. No, I'm being completely honest. I just, unintentionally tell you the non-truth, right? Oh, for whatever reason, my screen just died, so I'm gonna have to look at the projector to work on this program. All right, so let's go ahead and actually, do something with this program. We'll do a GCC-G, and you know what? I don't think warn all and pedantic is going to help you here, because C does not really do much checking when it comes to pointer arithmetic. It doesn't really say, oh, you know what? The way you're accessing this location seems to be a little bit wacky. I don't really think you should be doing this. Nah, C doesn't care. It just says, if you think you know what you're doing, go ahead. I'm all good. So we'll go ahead and see what this program is going to do. Find. Oh no, we're not dealing with findbacks, are we? Okay. So let's. Yep. Go ahead.
What other popular languages allow you to do that? Allow you to change that?
C++. C and C++ are two of the most dangerous programming languages. Unfortunately, most universities and colleges now use those as the de facto, standard programming language in all classes. You cannot do this in Java, because in Java you cannot have pointers to begin with, and when you have references, you cannot do arithmetics on references. You cannot say, I want to access what is after, what this thing refers to. Nope, you cannot do that, right? Visual Basic has no pointers either. In Pascal, they do have pointers, but they don't let you do arithmetics on pointers. So the worst thing you can possibly do with Pascal is to have a dangling pointer, with a data structure. It's just not initialized, okay? Which is not even close to, the nastiness of something that we just saw. Because, if you have a dangling pointer, then it's a static thing. The symptom is usually not too far away from the problem itself. This one can be very far away, because depending on the offset, you can be changing something that is literally hundreds of thousands of lines of execution later. And all right, so let's go ahead and write that program. So we'll write saboteur, which is actually the name of a movie, I found out.
Yeah, Hitchcock's.
Oh. I'm not a Hitchcock fan, so. Okay, so we'll go ahead and say saboteur and int x. Plus 1 plus equal to x. That's all it's going to do. And here is main. Main is going to have its own local variable x, local variable y, X gets, let's make it, very distinct, 42, and Y gets, 81, and then we call Salvatore 4, and then exit X here. All right, so there's our program, gcc-warn all -pedantic -g-o Salvatore C. Oh, it's just complaining that Y is not used, okay, but it really is. Unintentionally. Okay, so we'll run the program first, okay? When you run the program, it doesn't really show you anything because the command line does not show you the exit code of a program. So it's not going to show you anything. But when you run it in GDB, then it will tell you that, the exit code does not seem to make any sense. So if you run the entire program, it tells you the exit code is 244. I think I messed up something. It's not supposed to be 244, but it's definitely not 0. Okay, let's see, what did I mess up here? 244 is code.
It's 244 in octal, right?
244 is octal, so that is basically 4 plus 8, which is 12, plus 64. Doesn't make any sense. Okay, let me track this code. Okay, X gets 42, Y gets 81, Salvatore 4. We get into the subroutine $y plus 1, which is referring to OEBP, plus equal to X, which is 4 here. So when we exit with X, it should be exiting with the number in Y. Okay, let's do that again in GDB. This time we'll put a breakpoint. Salvatore. Put a breakpoint on line 14. Run the program. Find out what X is. And it is messed up, but not messed up the way that I think it should be. Okay, did I copy the code wrong in a way? In any way? No, I did not.
But you said before that Y before X is convention, not standard, right? So maybe.
Yeah, but it's the same compiler. One thing I did forget to do is to do the pound include. I don't think that's going to change anything, but we'll go ahead and do a pound include stdlib here. That can actually do it. Yeah, that can actually do it too. Okay, so we'll gcc again, gdb. It's also possible it might have. Okay, let's go ahead and GDB it. Put a breakpoint on line 14. Run the program. Print X, print Y, print ESP, print EBP. Okay, so this is how you should debug your program when you run into problems like this, is to print both of them, okay? And then we put a breakpoint on line 15 and just continue execution. So right now we print X again, we print Y again, and you can see that Y is now X, and X is something else. Okay, so what we have done is we're moving the frame pointer in the wrong direction. Okay, the other thing we can also do, let's go ahead and check EBP first. So you can definitely see that EBP is now 4 more than what it should be, because it was 9.8 before, now it's 9C, so it's off by 4. When you run the program in C, strictly, EBP should never change. Okay, you should never see EBP changing in the same invocation. So we are accessing X. Okay, so this is what we need to do. We print $X, we print $Y, and X has the higher address in this case. So that convention was not observed. Yep. When I did this at home, it actually worked the other way around. But the point is, it does change what you're accessing. Everything is now off by 4. except the assumption that x has a lower address did not hold in this case, because it's never part of the language standard that says if you declare a variable earlier, it has to have a lower address. That's never guaranteed. All right. Any questions about this? Okay, so you guys can pass your answer sheet in, and I'll count your answer. Do you need more time to write it? No? Okay. So have I collected all of them? All right. All right. So with your homework assignment, let's go ahead and go back to the homework assignment, because I do want to tell you what you're supposed to do with your homework assignment. Let's see, where is it? Oh, I have it on the command line already, so I just need to. This is a really useful command, push D and pop D. Now that we have talked about a stack, the command line has a stack of directories. So when you say push D, you're pushing the current directory on the stack, and then you're moving to whatever you're pushing as a parameter. So it's almost like calling, because you're pushing the current one on the stack, and then you're going to the directory, then you push D, that is an argument of push D, so that when you do a pop D, it will go back to the previous directory. And you can do this any number of times because it's a stack, right? So you can do it like 3 times, and then it will keep track of the history of where you have been. And I find it really useful. You might find it useful if you do a lot of system administrative work, because you have to go all over the place, and those paths are like really, really long, so you don't have to want to retype all the paths again and again.
You get an error message if you open up a new terminal and you do initially just do pop D?
It would just tell that there's nothing to pop to.
Okay.
So it says stack is empty. All right, so this is your homework assignment. So your homework assignment has a main file like this, okay? So the main file is really just, a test point. All it does is to call, find max n with different types of parameters, and with each instance, line 6, 7, and 8, it should find the maximum of the numbers that you pass. The minimum integer value is used as a terminator, so that's why it's always at the end. It is basically saying, okay, stop here, because there's no way the subroutine actually knows how many parameters there are on the stack. You need to have some kind of a terminator or a count, so that the subroutine knows how many things it should expect on the stack. Okay? So in this case, I use a terminator and not a count to indicate where to stop. So there's nothing too mysterious here. The mystery part is in find max n.c. This is the subroutine that you have to implement in assembly to replace it. Okay, so you are going to write a subroutine exactly the same name, find max n, but in assembly using a file find max n.s to write the subroutine. Okay, so what you will do is you also have to modify the makefile. And this is my quick introduction to the makefile. So this is I know it looks kind of nastier than your usual makefile, but this one is also very nice in a way, because all you have to do is to tell it what kind of C source files you have in your project, and what type of assembly source file you have in your project down here, and it will do the rest automatically. Okay, so let me demonstrate what I mean by that. So let's just say that we don't use find max n.c anymore, and you have to do the same thing when you do your homework assignment, and I move it down here. Okay, you don't have to do anything other than this. Okay, it's just the declaration you have to change. None of the rules have to change at all. So then we go exit the makefile, and I'll just go ahead and make a stub here. So find max n.s, and Remember to do a .global, because otherwise find max n as a label is not exported. The linker is going to have a problem finding it. So at this point, I'm not going to do much about it. All I'm going to do is to say, you know what, I'm just going to move a 0 into EAX as my return value, and then return. Okay? So I'm ignoring all of the parameters. You know, this is just a little stub function. And all you have to do is to say make. Missing separator, you mean tab instead of 8 spaces. Line 1 dot global. It doesn't have a problem with that. Okay, clean it up first. It's still having a problem.
I've got that problem with make files before. It's sensitive whether you use tab or space in make files.
Okay, it's the make file itself. Okay, gotcha. Oh, I forgot about that. Okay. It needs to have a a file for. I don't think it needs that. Maybe it does.
Say line 1 then. It'd say line 1 was the issue.
Yeah, but line 1 is not the. Well, it says no such file or directory. You know, main.d does not exist. Main.c is still here, and the executable name is main. We have one assembly source file with a .s extension. Okay, let's go ahead and change our convention and use uppercase S. It is significant. Okay, whether it's lowercase or uppercase, it is significant. But for our purpose, it should be okay. There we go. That was it. The uppercase S, means that it can go through the C preprocessor, and lowercase s means it does not go through the C preprocessor. But since I don't really have anything to do with the C preprocessor at this point, it's okay. It doesn't really hurt anything. So you just have to make the adjustment. Use uppercase S as the extension and not lowercase, and it will be okay. All right.
Can you talk briefly about the difference between the two conventions? Talk briefly about the difference between the two conventions.
One goes through CPP, the C preprocessor, and the other one does not. Uppercase does, and lowercase does not. All right. So that's your new homework assignment. You have 1 week and 2 days to work on it because of Thanksgiving. So I'm giving you guys a little bit longer time to work on this one. And we'll just take one more look at find maxn.c, and just to go through this and see whether we have everything that we need to know in order to get this done. The only part that you probably may need to think about it a little bit is int min. Okay, because int min is a macro defined in limits.h. Okay, and depending on what is in limits.h, you may not be able to include it in your assembly source file because it might contain something that has C syntax and not just pound define, pound define, pound define. We can give it a try. Okay, I'm going to give it a try first, just so that you don't have to kind of do the experiment yourself. So we'll go ahead. Oh, it's still using the C file. It's not using the assembly file because we don't have an assembly file with a uppercase S extension. So we'll go ahead and rename the one with lowercase to the one with uppercase, and we'll go ahead and say pound include limits.h here. Oh, it doesn't like that. Still using the C version. That is strange. Because we have the assembly file here. And it's still referring to the .c file. you're still using the .c file. I think the reason why it's doing this is because .c has a priority over .uppercase s. So when you replace the C function with an assembly function, you have to rename the .c one. Sorry about that. I forgot about the priority, because when it has two ways to make the same object file, it will pick one of two ways, and it will pick the .c over the .s file. So that means with the .c one, I have to kind of change the extension so it's no longer recognizable to the make file, as this is a source file, and that should. Remove all the dependencies files. Okay, now it works. Main is up to date. Yep, now it does work. Let's double check everything. Yep, so now it's okay. So there are a few things, I'm gonna change the tar file. I'll send you guys an email. How about this? I'll send you an email when I have the make file. Well, when I fix the instructions, it has to do with the instructions, not really the rules in the make file. But you can see that this time I can do a pound include inside the assembly language file, and that's only because it only contains pound defines, which are not which is not seen by the assembler itself. It is seen by the C preprocessor. Okay, when you took CISP360, the professor talked about the C preprocessor, what is a pound define and stuff like that. Okay, so pound define is a macro. It is a C preprocessor feature. What it does is you can do a pound define x1. Okay, so let's use that as an example. It will textually, locate every occurrence of uppercase X and replace it with just 1. Okay, but it doesn't really know the context of where X is and why it should be replaced with 1. That's just what it does. And it can do the same thing with assembly source code. It will just replace a particular macro name with the definition of the macro. And that's why this feature also works in assembly. Is that all right so far? Okay. Okay, so any questions about the assembly code itself? Okay, let's go back to the code here. Oops, I changed the extension. There we go. So getting back to this code here, line 2. Any issues on line 2? How to define the function, the entry point? Yep.
So you're taking in, other than the int x, you're taking in 3 other parameters? Is that what that's indicating?
No, it's indicating it has at least 1 parameter, but we don't know exactly how many there are. Okay, but x is the only one that has a name. The other parameters do not have names, so you will have to access the other parameters using their address. Okay, line 4, 5, are basically just declaration of local variables. One is a pointer, one is a keeping track of the maximum. Line 6 is just the initialization of maximum, because I'm guaranteed to have at least 1 number. So I can always say, let's assume that is the maximum. If I find anything bigger than that, then we'll update maximum. Okay. Line 7, it is taking the address of a local variable. Okay, that is something that is a little bit interesting. It's not something that we have not seen before. Okay, we have all the instructions that we need in order to implement line 7. So now the question is, how do we do it? Okay, so getting back to this picture here on the whiteboard, a local variable is really just something on the stack, right? And we should know how to access it based on its offset from where EBP points to. Is that okay? So, well, if you know EBP and you know how many bytes that thing is away from where EBP points to, don't you know, how to compute the address of that thing? Yep, so that's basically how you compute the address of a local variable. In this case, we store it into BPDR. Your code doesn't have to follow the C code exactly, so if you find that it is more convenient to use a register instead of a local variable as a pointer, go ahead, okay? Use CX, EDX, or EAX for that purpose. EBX is kind of special, so I would not touch EBX. If you do want to use EBX, save and restore it, just like EBP. Okay, because it is a little bit special. The compiler makes the assumption that EBX is also preserved for whatever reason. So that's line 7. Line 8 is comparing not the pointer itself to the smallest integer in 32-bit. It is comparing what the pointer points to the constant, which is the minimum integer value that can be represented in 32 bits. If you use EAX or one of the registers for PTR, that's easy, okay? Because you just need to use the indirect addressing mode to implement the access to the content or the value pointed to by PTR on line 8. Same thing on line 10, except on line 10, you're not comparing to a constant, you're comparing to max. If you use another register for max, that makes it very easy as well, okay? So if you don't feel like using local variables for PTR and max, and there are enough registers around, you can use registers for those purposes, which I think greatly simplifies your code. Line 12, we are storing whatever PTR points to into max, because basically at this point I have just found a parameter to find max n that is larger than the known maximum up to this point. So if I find something that is larger already, I should update it. Line 14 is plus PTR. This one you have to be careful because we are incrementing a pointer to an integer. So that means you're not going to add 1 to the register. You're going to add the size of an integer to the pointer. That's it. I mean, line 16 is returning max. The convention of GCC is the return value is in EAX. So you just have to copy whatever is storing the maximum into EAX on line 16, and you're done. All right. So are there any questions about find max n? No questions? It's all good? I don't think this one would take you too long, to implement, but it is kind of the tricky part is this one here, But if you just look at the rest of the code, it's not really anything that's too special. Okay. So now getting back to our main topic, we are kind of catching up, with the topics of this class. Oh, I somehow signed myself off. It's not a
incognito mode.
Hmm?
You're in incognito mode.
Oh, why would I be there? Okay, this one is not. So the next thing that I want to talk about, I have already changed the highlight to the section that we are in at this point. So we are now in topic 9, which talks about parameters, local variables, and the return value, which we have already just talked about. So it doesn't hurt to read those 2 linked pages, at this point, again, just to make sure that you get everything that needs to be understood with those things. So topic 9 is really kind of done, except for one thing, okay? The one thing that I have not talked about is how do you keep track of the offset to your parameters and also to your local variables. So I'll just kind of go over that a little bit because I think, in general, that will be helpful to your other projects. So what I'll do is I'm going to look at, well, I'll use find max n. I mean, why not? So we'll go ahead and look at find max n.c.back and also look at find max.n.c here, uppercase S, and we'll do it side by side. So this way we can see both the C code and also the assembly code. And no, I'm not going to do your homework assignment, but I will give you a little bit of a head start. That's what this is intended. Okay. So what I'll do is I'm going to define some labels, not macros, just labels. You can use macros for this purpose too, but I will just use labels, for this purpose. So what I'm going to do is to define some displacements, offsets, from where EBP points to various components of the call frame. Okay, and that's what these symbols are for. So ODBP is pointed to by EBP itself, so it is defined to be 0 as a label, which means ODBP is at a 0 displacement or 0 offset from where EBP points to. Is that okay? Because I just want to keep track of the call frame, okay, items on the call frame based on the displacement or offset from where EBP points to. Okay, so according to the C code, where is my parameter X? Well, what is next to old EBP? Where's the return address? If you look at the whiteboard, yep, right on top of it, but it's not 1, it is 4 bytes. So you have to kind of make sure that when you program in assembly code, you're counting in bytes. When you're programming in C and C++, it's counting in number of items based on the size. So return address is wherever OEBP is plus 4. Instead of just saying 4, I'm using an offset or relative mode. And then where's the parameter X? Parameter X will be 4 bytes on top of the return address. Okay. Are there any questions about how I define these symbols? No questions? Okay. And then what about my local variables? If I so decide to use local variables for PTR and max on the stack, where do you think how should I define the displacement to local variable PTR? Yep, old EBP minus 4 or minus 8, depending on the ordering. But you can always say this is minus 4, and then max is going to be PTR minus 4, because those two are local variables. So I'm not using the convention of whatever declare first has the lowest address. I'm just declaring these things in the order of when I encounter those things. And that's it. Okay. So this way, in your code, in find max n implemented in assembly language, now you don't have to mentally keep track of an offset of 8, an offset of 4, an offset of -4. You can now use the symbolic name to help you refer to various items on the call frame. Okay. So this is the only part that I have not talked about related to how to pass parameters on the stack and also how to access items on the stack frame. Okay. But this program, the C version at least, the way it is, also tells you why we push parameters backwards. In other words, why are we pushing the last parameter first so that it has the highest address? This is why, okay? Because in C, you can pass a variable number of parameters to a subroutine. So if you change the way we push the parameters and say we push the first parameter first, then we have a problem because we cannot access the first parameter not knowing how many parameters, what is the total number of parameters on the stack. Is that making any sense to me, to you? Okay. Okay, just think about it like this. If you look at Printf, okay, so I'm gonna use my text editor here to take a look at Printf, which is actually the first subroutine that can take on any number of parameters. It has at least one, which is the format string. So let's take a look at this one here. Okay, %d, \n, and the end quote here. Okay, and then obviously I have to give it 2 integers to print, so I can give it like 23 and 91 here. Okay, so this is my call in C. If I push the parameters like the first parameter is pushed first, then the address of the string is pushed first. And then I have any number of parameters after that. But from the subroutine's perspective, from Printf's perspective, it needs to find the format string first in order to find out how many other things should be on the stack. Is that making any sense? So that's why we cannot push parameters pushing the first parameter first, because I don't know the offset to the first parameter if I did things that way. On the other hand, if I push 91 first, the 91 has the highest address. Then I push 23, it has the lower it has a lower address. And then I push the address of the string, which now it has the lowest address. It's right next to the return address, right, of the subroutine. I can always get to the first parameter then. And once I scan the format string, then I can decide, oh, okay, I can see that the first %d is going to be specified by the next parameter, which is supposed to be an integer, and then the one after that, which is 91, is going to fill the second slot or the second placeholder %d in the format string. That is why in C and C++, parameters are always pushed backwards. Now, is that a common thing across all programming languages? The answer is no. In Pascal, it's exactly the opposite. The first parameter is pushed first. It has the highest address. And that is why in Pascal, you do not see anything like this. There's nothing, it is not possible to take on a variable number of parameters as a result. Any questions about that? And has anyone programmed in Windows, like tried to write a GUI program in C or C++ in Windows? And do you recall that you have a word like Pascal, underscore Pascal in the source code somewhere?
Yeah.
That's because underneath Windows is using that particular convention. So when you use the word underscore uppercase Pascal, you're telling this Microsoft compiler and say, don't use the C way of pushing parameters, switch to the Pascal convention to push parameters.
They don't like the C way?
I think it's because Windows was probably written in Pascal, at a very, very, very early stage. So, that became the convention. They have to follow that convention after that. Yep.
So how would the stack look if we were to put the on the stack?
With this one?
Yeah.
With this one, the stack would look like, we have 91 represented as a 32-bit number, 23 represented as a 32-bit number, and then we have some kind of address here, and that address is going to point to a string of %d, and the line feed character. And then after that, we have the actual return address. And from the call list perspective, if printf is implemented like all the other type of subroutines, then we can always expect ODBP to be here, and then a whole bunch of local variables. But since I don't see the actual definition of printf, I don't know how many local variables it has. So this is the picture that I know for sure is going to be the call frame. What I cannot tell is, what are the local variables in printf. But this is exactly why, we have to push the parameters backwards, because EBP always points to this location. As a result, it always has a way to get to the first parameter in this case. But once I get to the first parameter, I can now, access all the subsequent parameters if I need to. Questions? Did I answer your question?
Yes.
Okay, good. All right, so if there are no questions, I'm gonna stop here, and then I'll go to the lab. Since, this is the last class meeting before Thanksgiving, I think we should get the homework assignment done today so that you guys can have a more relaxing, Thanksgiving.
I agree.
And then you can use then you can use Black Friday to go shopping and watch the movie, The Imitation Game. The Imitation Game, which is a story or movie based on Alan Turing. Yes.
I wanted to see that.
Yeah, it's I think it's a really good movie for us, to watch, just to remember, how computers came to be the ones that we use now.